All right. So we change tack again. This time we go to quantum refinement. We stay in Sweden, so we don't change country for now. And Ulf Ryde is going to talk us about improvement protein structures by quantum refinement. Start on.
Okay. Thank you very much, the organizers, for inviting me to this very interesting conference and to giving me the opportunity to tell you a little bit about quantum refinement. And the outline of my talk is very simple. I will describe the method, then some applications, and then finally some extensions to different methods. So first of all, I should say that I'm not a crystallographer at all. I'm a computational chemist, quantum chemist mainly. So to start, I will give you a very short introduction to computational chemistry. We have heard a little bit about computational chemistry today. Perhaps it's a bit obsolete. But when doing computational chemistry, the main method is quantum mechanics, because that's the truth. So well, by solving the Schrödinger equation, you get the energy directly and you get the wave function. And from the wave function, you can get anything you want to know about the system. It doesn't contain any parameters, and but you cannot solve it for anything bigger than 1 electron exactly. You can solve it approximately, and the current favorite method is a DFT method, density functional theory, for which you can use up to, say, 1,000 atoms, or geometry optimization 400 atoms or something like that. If that's too expensive, you turn to what we call molecular mechanics methods. Then you don't care about Schrödinger equation, you don't care about electrons. You consider your molecule as balls and springs, essentially. And then you have the empirical potential energy function, which could be, in principle, any function that gives you the energy as a function of the coordinates. But typically for proteins, we have something like the one we heard about before: bond angles, dihedrals, van der Waals interactions, and electrostatics, although in crystallography, we normally ignore electrostatics, which is a problem because that's often the most important thing. But with molecular mechanics, you can do millions of atoms, but you need to parameterize it. And typically, it's less accurate than quantum mechanics because you don't include everything important. And if you want to combine the best of these two worlds in computational chemistry, you use the QMM methods, then you use quantum mechanics for a central system, small but interesting system, for example, where reaction take place. And then you have molecular mechanics for the rest, and you do that by adding the energies and forces and ensure that you don't double count anything. So then we do quantum refinement. So what I say is that we don't do any crystallography ourselves. We take structures from other people, and then we just redo the last step, the refinement part or the structures. And crystallographic refinement, you could say that then you optimize a pseudo energy function. We describe how close you are to the crystallographic raw data, for example, R factors or something more sophisticated. So that's part of the energy function. But normally you combine this with what you call empirical restraints, which from the computational language is a molecular mechanics energy function. And since they are two different terms with different units, you need to weight them. And you can use a weight factor to bias it towards crystallography or bias it towards the restraints. And from a why do you need these restraints? And that's because the low and medium resolution structures, you don't have enough information to tell you where to put the atoms exactly. So you could say that to get the right bond length and right angles, you need this empirical potential. If you have a bad structure, you could look something like this without empirical potential. And then if you add the potential, you get the chemical structure back. And you should always remember that this takes the structure away from the crystallographic raw data. So the R factor will increase a little bit, but very little if you do it only for a small site. If you do it for the whole protein, it starts to be significantly. Okay, so from a computational point of view, there are several problems with using these empirical potentials. One problem is that, as I said, molecular mechanics is not the best method we have, and we know that we are missing terms, for example, the electrostatics term. The second problem is that the result, of course, depends on the molecular mechanics potential. So the structure is no longer an experimental structure, it's a mixture of computational and experimental structure. And if you have a bad potential, you get the bad structure. That's natural. And perhaps the biggest problem is that if you have that the quality of a structure is different at different parts of the structure. For the amino acids, you have good potential based on lots of statistics of the crystal structure. So that part is perfect. But for the interesting part of the system, so for the substrate inhibitors, drug candidates, or metal sites, or in neutron structures, the protons, you have much less information, and therefore the structure is much more inaccurate. And how can you solve these problems? Well, already 20 years ago, we suggested to do the same thing as we do in computational chemistry. We replace the molecular mechanics or the empirical restraints with a QMMM energy function for a small but interesting part of the protein. For example, the active site. And that's what we call quantum refinement. So it's a very simple method. We do, in principle, a QMMM geometry optimization, but within the crystallographic refinement program. So we do refine the structure with both quantum chemistry and crystallographic restraints. And does this work? To show that it's not easy because, as I said, the restraints will always bring you away from the crystal structure. So to show it, we decided to use a structure where, or the same protein where we have two different resolutions, two different structures of different resolutions, one medium resolution and one very high resolution where you don't really need the empirical restraints. And then we use the data of the medium resolution structure and see if we can bring it closer to the atomic resolution structure. And then we need something that is interesting for us. So we have a metal site here, cytochrome C553, contains an ion in the porphyrin, and then a histidine and a methionine in ligand. And there is quite big differences between the two structures, 0.3 angstrom, for example, for the ion-nitrogen distance. And by using only the lower resolution data, we can bring it very close to the high resolution structure without using any data from the high resolution structure. And the reason for this is, of course, that the quantum chemistry already from the beginning give very good results. And that's the basis of quantum refinement. We need a quantum chemical method that gives you results that are close to the truth. We have typical DFT methods we're using have an accuracy of 0.02 to 0.05 angstrom for metal ligand distances. So applications, what can we use it for? And as we heard in the previous talk, the important thing is often what you don't see in the crystal structures. So for example, the protons we don't see. So could we not see the protons, but could we deduce where the protons are? And that's rather easy for metal-bound water or solvent molecules, because if we have a water, OH or O2 minus make a quite big difference in the distances to the metal once you know what it should be with the different ligands. So to show that this works, we took alcohol dehydrogenase, where we have kinetic data showing what is the pKa value or the metal-bound molecule. So the alcohol dehydrogenase contains a zinc ion with 2 cysteines, 1 histidine, and then a solvent molecule or a substrate molecule. And depending on the coenzyme and on whether we have a alcohol or water molecule, we get different pKa values. And then we selected a crystal structure for this NAD+ complex with an alcohol, which should have a pKa of 6, and the structure is collected at 8, so it should be an alkoxide, deprotonated alcohol. And then we do a quantum refinement with both the alcohol, so with the proton, and with the alkoxide, and see which of the two structure fits the experimental data best. And we do it with different weight factors just to see how it reacts with different weight factors. And we can look at the R3 value. R3 is not a very good measure for small changes. We use better measures, as you will see soon today, but this is an old study. But we can see that the R3 is a little bit better for alkoxide than for the alcohol. We can look at the zinc-oxygen distance, which should be the distance that differs mostly between the water and the OH, or the alcohol and the alkoxide. And we can see that for the alkoxide, the distance is always close to what we find for the quantum chemical calculations in vacuum, whereas with the alcohol, it goes slowly from the vacuum value, from the vacuum value down to a value in the crystal structure. So it's far from the crystal value. So it shows that it doesn't fit the structure. And finally, we can look at the strain energy, which is a quantum chemical energy of the quantum system optimized in vacuum or optimized in the crystal structure. So it tells us how much the crystal structure strains the active site. And we can see that it's always lower for the alkoxide than for the alcohol. So all three criteria point out that this should be an alkoxide in agreement with the kinetic data. And we can also look at the original crystal structure. There are the zinc-oxygen distances in between what we expect for the alcohol and for the alkoxide. So we could not really tell it directly from the crystal structure. Then some other applications of this method, we could interpret what's structure, or what we really see in the structure. So I will talk a little bit about the particulate methane monoxidase. It's an enzyme that converts methane to methanol. And it's a strange protein. It's a membrane bound, and there is no real consensus of what is the active site and what they do look like. When we did this structure, or with this study some 6-8 years ago, there were only very bad crystal structures of about 2.8 angstrom resolution. And they show really crazy copper structures. So they have two copper ions and they are close together and they don't have ligands, and the ligands don't point towards the metals. So clearly something is wrong, and we thought that we could sort this out. So we started to do quantum refinement with different combinations. We added water molecules to get more ligands, but still we got only crazy structures until we simply removed one of the copper ions. And then you get a completely normal, almost square planar copper site, and this little blob here, which they interpreted as the second copper ion, there we can fit very well water molecules. So this is a mononuclear copper site. And that was confirmed by experiments later on. And we switched to a much more complicated enzyme. We heard a little bit about nitrogenase yesterday, I think. So that's an enzyme that breaks down the NN bond in N2, forming ammoniac. To do that, we have a very big cluster containing 1 molybdenum 7 ions, 9 sulfide ions, a central carbide, so C4 minus, 9 sulfur ions, and then a homocitrate ligand. And we wanted to do quantum chemical studies of this, and then we need to know exactly where are the protons in the structure, and especially we need to know what is the protonation state of homocitrate. And homocitrate contains 3 carboxylate groups and then an alcohol. So you could imagine that it's 3-, but then the alcohol is binding to the metal, then it could be deprotonated, so 4-. And then if you look at the structure close to it, it looks like that one of the carboxylate groups might be protonated. So we have 4 possible protonation states. And then once again, we do quantum refinement with the 4 protonation states, see which one fits the crystallographic raw data best. 2 of them gave very bad RSCD factor. So that's the better measure of the local real space fit or the density. So 2 of them are really bad, but 2 of them gave almost the same RSCD scores. One of them has a single proton that is actually shared between these 2 oxygen atoms. The molybdenum is up here. And the other one contains another proton on this side. And if you protonate here, then the carboxylate group swings a little bit like that. And then the crystallography says immediately, no, that's not true. You have too much oxygen here, too little oxygen on the other side. So we can directly say that this is the correct protonation state. And that's very important if you do quantum chemical calculations on it. This is another study of the nitrogenase where they said that they see N2 intermediate because we don't know where N2 binds to this site. We only know the resting state. But in this structure, they showed that in one subunit, they said that they had 1 N2 replacing one of the breaching sulfide ions. And in the other subunit, they had 2 N2 binding to the other 2 breaching N2 ions. And this was a structure at 1.8 angstrom, but it looks quite strange. And if you look at it more closely, you see that it's great, very anisotropic, and that the resolution is very bad along some of the axes. And then they have reinforced the anisotropy by using anisotropic B factors, giving these layered structures of densities. If you redo it with quantum refinement and normal isotropic R factors, you get a better structure, but still not perfect around the N2. And if you replace N2 by the sulfur that is in the resting structure, you get something that is better. So there is actually no support of N2 binding to this active site. So that's some examples of what you can do. Typically, we compare different structures and see which one is the best one. We can extend it. So what I showed you up to now is X-ray crystallography, but we could do the same thing with neutron crystallography. That works exactly the same. Can do both only neutron, but also joint refinement, as we heard about before. And we can, for example, tell you a little bit about where are the protons, because it's not always you see the protons clearly in neutron structures. We can do the same thing with NMR structures. Then it works equally well because you have the same type of energy function where you can replace the MM term with a QMMM term. You have other types of structures. You have ensembles of structures, but you can still, for example, discuss calcium sites in a protein and see what they would look like in an NMR structure. We have also done XSAFs, which is totally different. So extended X-ray absorption fine structure. You normally do it only for single metal sites, and the only thing you get is distances between the metal and the ligands in shells. But you can use the QMM calculation to give you the atomic position of everything, and then you get the multiple scattering much better. And once again, you can tell which of different structural hypotheses fits the experimental data best. Then I will tell you a little bit about the recent developments. So when we did this 20 years ago, we used what the crystallographers at the department recommended us. So that was the CNS program. And we used the Turbonville program for quantum chemical calculations. But since then, CNS is outdated and Turbonville has become commercial. So we wanted to do something else. And that has been a struggle for over 12 years to implement quantum refinement in Phoenix, to change from tunable to a free, where quantum software like Orca took 1 or 2 days. But implementing this in Phoenix has been a pain, but thanks to a very good student, Christopher, we finally managed to do it, and that opens a new world for us. Then we can do all the structures available in Phoenix, including cryo-EM. So the last, or the second last application I will show you is quantum refinement in cryo-EM. So then we move back to the PMMO with the caposites, because there have recently been 2 groups of cryo-EM structures, or the PMMO. They come from the 2 competing groups. One group who says that the active site is one of the mononuclear caposites. The other group saying that it's instead a 3-nuclear caposite that is not seen in the crystal structures. And they show quite different things. I will just show you a few of the caposites here. The capo B sites is the one I showed you before. And the interesting thing is that in one of the cryo-EM structures is still a mononuclear site, like in the crystal structures. But in the other structure, they again make it binuclear. But once again, the structure is crazy. You have a very short distances to the ligands, and you have a very short kappa-kappa bond. And once again, if we do it with 1 kappa, we get a much more reasonable structure. But you can also see that whatever we do with the structure, the real space correlation coefficients goes down. And I will comment on that later on. Then I take one of the extra caposites seen in only one of the structures. They called it the kappa sponge. And once again, they show a very, very strange caposite. If you can see that there is only 1 real ligand. There is an arginine ligand very close to the kappa. There is actually 2 arginine ligands close to it. And if you put in a metal in it and do quantum refinement, it moves directly out of the density to optimize this interaction with the single ligand there are. But it doesn't still look like a caposite. But if you instead put in a water molecule there, then you get a very nice hydrogen bond network. Everything fits fine. And yeah, you get a real space correlation coefficient that is a little bit better than the caposite, but still worse than the original structure. And if you think of it first, it might be sad that something moves out of the density, but if you think more about it, it's rather natural, because all the normal atoms, the amino acid atoms, they are restrained by the empirical potential, but the metal sites and the water molecules, they are not, because you don't have any good empirical potential for it. And if you compare how much they move out of the density, that they are exactly the same as for the protein atoms. So the 50% of the protein atoms move more out of the density than the metal and water molecules do. So we will argue that quantum refinement is the proper way to treat metals and water in cryo-EM structures. Yeah, I just say that we can do also electron crystallography. It's a little bit different, but it works, and we have done the first application. I don't say anything about the result. We can differ between water and OH, but not really between OH and O2- there. So finally, conclusions. I hope I have shown you that quantum refinement shows you an ideal compromise between quantum chemistry and crystallography. You can use it to interpret, and you can use it to improve structures. You can determine protonation states. I didn't show you, but we can also see what oxidation states we have. We can make structural discrimination between competitive structures. We have extended it to many different methods. And we think that this is, or we have shown that it's ideal to use for metal sites, for protons in neutron structures. we started to look at serial crystallography, where you often have overlapping structures, and then you really need a good potential, especially if you have a reaction intermediate with unnormal geometry. And finally, I want to thank those who did the job we have at the conference, both Justin, who was my previous student, and Christopher, who is my current student doing this. And finally, I want to thank these for money, these for computer time, and of course, especially the organizers of this wonderful conference. And finally, all of you for your kind attention.
Thank you, Ulf. We have time for maybe one or two questions. So anyone has a interesting question? I don't know if there's any questions on Slack. James.
James Holton, UCSF. How would this work with radiation damage? What if I add an extra electron or take one away?
So I have some slides about that, but this is very sensitive to damage. So you can use it to see damage. Because as we heard before, the first thing the electrons do, they go to the metals. And we normally look at the metals, and there is a big difference between the oxidized and reduced metal. So it's important.
Hi, Alan Orville, Diamond Light Source. Thank you. That was great. No surprise for my question. I'd love to incorporate emission spectroscopy into the refinement and along the lines of the reaction coordinates. I mean, the XFEL work is something that we're quite interested in. I want to refine not just one structure, but this structure in context with its neighbors in a time-resolved process. Are you thinking along these lines too? Or is it still an individual structure on a refinement basis?
We haven't thought too much about it. So we have thought about doing time-resolved structure. So we really started to do it, and we can do it. We can do several quantum chemical systems on top of each other. And then you really need the quantum chemistry to get the right structure. To do many structures we haven't thought of, but if you have an energy function you can optimize, then it's no problem to do it.
Mike Wall, Los Alamos National Lab. So the quantum refinement as it stands is used to refine the geometry. You also have the electronic structure. So do you have something that you're working on or is incorporated to include the electronic structure through, say, Hirschfeld atom refinement or some other means to use the information about the electronic structure?
So of course we immediately get the electronic structures, so we could use it. We have, especially Justin, worked on the other problem with the independent atomic model, so the spherical scattering factors, which are problems. For example, you saw the molybdenum gave lots of difference density, and the same applies for hydrogen atoms in neutron structures. So we have done that with the Hirschfeld atom refinement, but we haven't combined the two methods yet. But it shouldn't be any problem to do it if we find the right software that can do it at the same time. Unfortunately, Hirschfeld atom refinement is mainly for small molecules and not for proteins, but that might change.
All right, if there is no more questions, let's thank Ulf again. And can I ask you to thank all the speakers for this session as well, for these 4 sessions, because then we'll go for the discussion. So can we thank again all speakers?